Welcome to the fifth and final video in our Class 19 series of lecture videos. In our fourth lecture video, we ended looking at how to convert alcohols to alkyl bromides, and specifically we explored the use of phosphorus tribromide as a reagent to convert secondary alcohols to secondary alkyl bromides through an SN2 mechanism. So we'll start this video off considering how to convert secondary alcohols to secondary alkyl chlorides. So how about making alkyl chlorides? Here we start with isopropyl alcohol. We'd use a reagent called thionyl chloride, so SOCl2, to convert that alcohol to a chlorine. And our byproducts would be sulfur dioxide and HCl. This is also an SN2 mechanism. Sulfur is also an oxophile, just like phosphorus. That must be why they put phosphorus and sulfur in matches. Here we have our oxygen taking a lone pair, attacking the sulfur, kicking a chloride out. And then that chloride goes and in an SN2 mechanism, pushes out our leaving group, which kind of looks almost like sulfur dioxide and HCl, but another molecule of our alcohol, or isopropyl alcohol, comes along, deprotonates it, and that kicks out chloride. So our SO2 bubbles up, and we've got protonated isopropyl alcohol and Cl-, which is what HCl would do in isopropyl alcohol. It would simply dissociate and protonate the alcohol. But we did convert some of our isopropanol to this 2-chloropropane. So, last page of notes for this last lecture video. I think we've talked about the Williamson ether synthesis. It's an SN2 reaction. It's very efficient. We take something like sodium hydride to deprotonate an alcohol. We lose hydrogen gas. We generate an alkoxide, a sodium alkoxide. If we throw in a good carbon electrophile for the SN2 reaction, like methyl iodide or some methyl halide, we'll get an SN2 reaction. And in this case, we form methyl terbutyl ether. We form a little bit of inorganic sodium iodide salt in this particular example. Intramolecular SN2 is faster than intermolecular SN2. So if we have a molecule that has both a hydroxyl group and a good leaving group on it, we could throw in sodium hydride, deprotonate that hydroxyl group, and instead of that alkoxide attacking another molecule, it will just swing shut faster to give us an intramolecular SN2 reaction. In this case, it gave us this 6-membered cyclic ether. In terms of ring formation, 3-membered, 5-membered, and 6-membered rings are fast. 3-membered rings are the fastest, believe it or not. 7-membered and 8-membered rings are generally slow. 4-membered rings are somewhere in between. So this is symbolizing reaction rate constant K, and N just means the ring size that we're talking about. So those rate constants are high for 3, 5, and 6-membered rings. So that means forming those ring sizes is fastest. And then, of course, 7, 8-membered rings are slow. So what you have to do if you're running an intramolecular reaction is, and you don't want competing intermolecular products, you need to make sure your reaction is dilute if you're forming 7 or 8-membered rings to slow down the potential for the intermolecular reaction and to give your molecule time to do the intramolecular reaction. So that pretty much finishes our 5th and final video. Good luck with the question, and I'm going to go start recording your Class 20 time series of lecture videos.